Swayam Prabha. Digital India. Educated India.
So, in order to understand what is this group velocity and phase velocity, so we saw that Vp is given by omega upon beta. So say at any point omega upon beta, if I draw a chord from the origin to any point, then this will be omega and this will be beta. So the slope of the chordal slope is equal to Vp, and Vg, the group velocity, is given by so I can define it as the slope of the tangent at a point. So at this point, if this red line is representing the tangent to the curve, Vg is the slope of the tangent at that point. Now, a dispersive media is a media where Vg is Vg changes with frequency. So, for example, coming back to the two curves that I had drawn, so this is for free space and this is for waveguide. To merge with it. So you see that for the free space, this is omega and this is beta. For the dispersion curve for free space, Vg, both Vg and Vp are constant. Whereas for this waveguide, this one, Vg and Vp change with frequency. Okay, so in other words, this free space is non-dispersive, but but my waveguide is a dispersive media when we are transmitting in the TM or TE mode. For example, for a parallel plate waveguide, when we are transmitting in the TEM mode, it is non-dispersive because there also the curve is, the line is straight. So for Vg to be constant, it is all you need is that the dispersion curve be a straight line. So for example, if we have a dispersion curve like this, where this curve is not passing through the origin but is a straight line, then Vg is constant, but Vp may not be constant. Why? Because the chordal slope, if I take the chordal slope to the various points, it is changing. One more thing I want to state is that remember in the past lectures I had said that Vp can be greater than 1 is the speed of light. It can be greater because see here consider this line. Here the chordal slope is greater than that of this line. Now this line, the slope for this line, Vp and Vg are same and equal to the speed of light, but this line has a higher slope than this line. Hence, the Vp at this frequency, the frequency corresponding to this point, can be higher than the speed of light. Okay, so I will just try to emphasize, try to show you how we can get the equation for the electromagnetic wave using the two Helmholtz equations that we had described. So let me go back to the Helmholtz equation. So I have been talking about the concept of beta without deriving the equation. That's because I assume that you already know what the equation of an electromagnetic wave is, but here we will go into more depth and exactly try to derive it. The solution of the equation is assuming sinusoidal time dependence. So this is the two equations. You see that both for the electrical and magnetic waves, there are actually two waves, one traveling in the forward z direction, other traveling in the negative z direction. And the beta value is given by this. So this is how that beta value comes out to be. This is that actually we can be shown that beta squared is equal to omega square mu epsilon. That's how the beta. So all along we have been talking about beta, and then from here we saw that C comes out to be equal to 1 upon mu 0 epsilon 0. That's how the speed of light comes. Now, when we discuss transmission lines, we shall be finding something similar, two equations for voltage and current, which are very similar. And there we'll see that beta comes out to be equal to LC, where L and C are the inductance and capacitance per unit length along the transmission line. And so from here, then we can have an equivalence that mu epsilon is equal to square root of LC. So this mu epsilon, which comes from an electromagnetic concept, and this LC, which comes from a transmission line concept, are equivalent. And in fact, the one way of defining the mu of a media is the inductance per unit length in a transmission line, and comprising of an ideal I beg your pardon, mu is the inductance per unit length of a transmission line, of a lossless transmission line in free space, and epsilon is the capacitance per unit length of a lossless transmission line. So these are some alternate definitions of mu and epsilon. Okay, now in the notes I have shown how you can, you can derive these wave equations, the voltage and current waveforms from these equations. I don't want to go into the detailed derivation, you can have a look at it. Now, one important component that we frequently use in our microwave theory is a microstrip line. So microstrip line, I have already mentioned earlier that it is very similar to a PCB board. A microstrip line is very similar to a PCB board, and it comprises of two metal layers. Metal. And this is a substrate. Now, because this is a two-conductor wire, we have to, from our electromagnetic theory, the transmission should be TEM, right? But in reality, what actually flows is what is known as quasi-TEM. That's because even though this consists of, this has a structure like this, we can analyze this in this way. So if we take the view from this point, the structure of the microstrip line comes out to be something like this. Suppose, so epsilon 0, so this is, it is surrounded on all sides by air. This whole structure is surrounded by air. Let's say the permittivity of the material of the substrate is epsilon 1, and permittivity of air or free space is epsilon 0. And let's say under this circumstances, the capacitance between the top metal and bottom layer comes out to be C. Then now suppose let us take an equivalent case that instead of this two dielectric layers, suppose we replace all space between the two metals and also elsewhere by a single dielectric having so what I am saying is that so here in this case, I replace the epsilon air and the substrate between the two plates by a dielectric having dielectric constant epsilon effective, such that the capacitance between the top and bottom layers still continues to be C. And say in the third case, I have just air between the top and bottom metal plates. So everywhere there is air, there is no equivalent dielectric or even the original dielectric. And say the capacitance between the top and bottom metal layers comes out to be C0 in this case. So what I'm trying to do here is, since this is a complicated, this particular scenario is a complicated scenario because we have two dielectrics. how do you analyze the TEM wave propagation in two dielectrics? To simplify that, what we do is we assume that instead of two dielectrics, there is only a single dielectric having permittivity epsilon effective, that is covering all space and beyond between the two top and bottom metal layers. So here then we can say, that so we have capacitance is given by this formula, right? Where D is the spacing between the top and bottom layers, bottom metal layers, and A is the area under the top metal layers. So from here we can say that C upon epsilon, so let me write it as C0 is equal to epsilon 0 A upon D, and C equal to epsilon effective A upon D. So here from here I have C0 upon epsilon 0 equal to A upon D, and from here I have C upon epsilon effective is equal to A upon D. So from here we have C0 upon epsilon 0 is equal to C upon epsilon effective, which implies epsilon effective is equal to epsilon 0 C upon C0. So this is how we can find out the value of epsilon effective. And as I said, the value of the transmission is in the form of TEM wave, if we assume that all epsilon 0 and epsilon 1 has been replaced by epsilon effective, and such a transmission mode is called a quasi-transmission mode. Now later when we'll study transmission lines, we shall come across two equations. One is which we already know, and the other is characteristic impedance, which we shall find that it is given like this. So Vp is the phase velocity, which in our case is equal to the speed of light, and capital C. And capital C is the capacitance per unit length. And so this becomes equal to this is an important concept for transmission lines, which we shall come across in the next chapter. This is known as characteristic impedance. So for now, just take it from me that this is the formula, and the value of the characteristic impedance for a microstrip line is given by this expression. So here this C is not this C, it is cap And finally, one important concept which I mentioned earlier is that since we have single conductor waveguides in microwave engineering, the concept of voltage and current can be uniquely defined only for two conductor waveguides. For single conductor waveguides, we don't have any concept of voltage or current because we cannot define them uniquely. Instead, we just have the concept of power. There's something called power transmission that is for real in whether it's a single conductor waveguide or a two conductor waveguide. And one more concept which is also valid is what is known as impedance. So even though voltage and current don't make much sense, and in any case they are very difficult to measure at these high frequencies where the parasitic values are quite high, impedance does have a meaning. So impedance, for example, if you consider your waveguide, what is the impedance value? So one way to define the impedance is, say, for a TE mode, we can define it as the ratio of the electric to magnetic fields, and the value that we get is like this. Okay, so beta corresponds to the propagation constant corresponds to the beta for the TE10 mode. Eta is what is known as the intrinsic impedance and is given as like this. And K, we all know what is the value of K. So you see that beta, if I write it this way, then actually we know that beta will be changing with frequency, right? Beta is not constant. Beta varies with frequency. We call the dispersion diagram where beta and omega are plotted. So if beta changes with frequency, then Z0 also should change with frequency, and which is what we don't want. We always want the impedance to be uniquely defined. So what we do is for these waveguides where even the ratio of Ex to Hy vary with frequency, we tend to choose a particular value. And once we choose the value, we use it constantly to design the circuit. Because we have to choose, because as you can see that this is not uniquely defined, right? So we need to find one particular value which is convenient, which is within range, and which can be used throughout the design. The other kind of impedance, so there are three different types of definition of impedance. Okay, one is this one, which is the ratio of the electric to magnetic field and is used for waveguide. So here, once again, I just repeat, we fix the value of Z0, say for a particular frequency, say the operating frequency that say the frequency that is most commonly used, we fix the value of Z0 at that frequency. And if our frequency of operation changes, then we continue using the same value of Z0. Another kind of impedance is this eta, which is used for free space. This is known as intrinsic impedance. Now this is purely due to the properties of the medium. You see, you can see that this has the dimension of ohms. It has the same dimension as that of impedance. So this definition of impedance is used only for media. In fact, the antennas, which are used to transmit to the atmosphere, often they are represented like this. So we have a source. This is the antenna resistance, and this intrinsic impedance is actually a load. The value of this for free space comes out to 377 ohms. Okay, and the third definition is already what we already know, that Z. Okay, when we discuss transmission lines, we will be using this definition. Now you might say that why are we using this definition when I just said that voltage and current don't make much sense? The reason why this still makes sense is that even though voltage and current don't make much sense, there are some things that we will still be continuing to use. For example, say whichever transmission line, whether it's like a parallel plate waveguide, a two-wire conductor, twisted pair, or even a single wire conductor like the rectangular or cylindrical waveguides, they will have certain concepts like beta and Z0. So these two parameters will be true for any waveguide or any transmission line or any distributed network, even if it is a single conductor waveguide, as you saw. So for a rectangular waveguide beta, we have a value of propagation constant that comes from Maxwell's equations. For say a two-wire conductor, we can have a value of beta that comes from the voltage versus current relationship, as we will see in the next chapter when we discuss transmission line. So whatever be your distributed conductor, these two parameters, beta and Z0, will definitely exist. Okay, because these exist, so we can then model any waveguide or two-wire conductor as a transmission line. So this transmission line becomes a theoretical concept, and the voltages and currents associated with the transmission line are just theoretical concepts for helping us solve distributed circuits. Okay, is that clear? So when we will discuss transmission lines and when we will discuss the voltages and currents, so these voltages and currents, if we can measure the voltages and currents, then they will directly correspond to those V and I that we discuss in transmission line theory. But suppose we are modeling a waveguide using a transmission line theory, then that V and I that are used in the transmission line theory are just theoretical concepts to help us analyze the distributed circuits. Is that clear? So with that, we come to an end to this chapter.